Greetings, ladies and gentlemen. Welcome to TV Math Hub. This channel covers different kinds of mathematics, starting from O level, A level, up to university level mathematics. For those that are here for the first time, please kindly subscribe to TV Math Hub so you can always get updated whenever a new video is uploaded. So here there are different videos regarding mathematics. So if you are interested in any kind of topic, any exams type questions and answers, please simply check through some of the videos that have been uploaded. Most of the videos have been uploaded to help you during your examinations. So for those of bed P, here is the playlist consisting of all the videos that you are required to go through. So here is the playlist. So far, 3 video lectures have been uploaded. And for that case, you need to go through all these videos. So whichever video that has been uploaded, please make sure you give it time and go through that video. Then for those of bed yes, still, you also have your playlist here. This is the playlist for bed yes. So simply come to the playlist, then check some of the videos that have been uploaded. So far, also 3 lectures have been uploaded. So ensure that you go through some of these videos. Make sure that you have a pen, you have a book, and make sure that you put down whatever is discussed within these videos. So far, we have looked at 3 lectures, and I believe we are moving at the same pace. Please don't forget to put the comment. In case of anything, simply put in the comment section. Maybe a number is not clear, maybe something is not clear, you would need some elaboration. Make sure you put the feedback in the comment section. So whenever I go through the comment section, I should be able to know whether we are moving at the same pace or not. Otherwise, I want to welcome all of you to our 4th lecture that will be building on basically where we stopped in our previous lecture. Ensure you subscribe, you like, and make sure you inform all your friends. Share this video to all your friends such that everyone is able to benefit to these lectures. Thank you so much. Let us look at our today's lecture. We shall begin our lecture number 4 by looking at what we call conditional events. Here we shall be considering 2 events A and B, where at times it is impossible for any one of the 2 events to occur without another. So in such a case, the preconceived idea about the one which has occurred would help you greatly to ascertain the occurrences of the other. So here you are talking about 2 events occurring, but the occurrence of one event has a condition that for it to occur, then one other event must have occurred, or another event must occur. So when you put a condition on an event, then the events you are considering are what we call the conditional events. And the conditional probability will be that probability that is computed under the assumption that some condition holds. So that is what we call the conditional probability. Then the probability that an event A will occur given that another event B has occurred is what we shall be calling the conditional probability of A given B. So whenever you hear the word the probability of A given B, that means that the occurrence of A will happen if B has already occurred. That is the probability of A given B, that A will occur when B has already occurred. And we shall be writing that as P of A, this is given B. This means that this was the first event to occur, and this is the event which is occurring after B has already occurred. So that is what we call the conditional probability of A given B. So when you write probability of A given B, this will be read as probability of A given B. This which is given, so that is A given B, this one here is the event which occurs first, and this one occurs later. So that's why we say it is probability of A given B. And how shall we be treating this? We shall be treating this as the probability of B intersection A divided by the probability of B. So we shall be denoting or writing the probability of A given B as the probability of B, remember B occurred first, intersection A divided by the probability of B. And this must be true if only when the probability of B is not equal to 0. Otherwise, when it is equal to 0, then the probability of A given B will be undefined. So whenever you meet this one here, the probability of A given B, then it will be treated as the probability of B intersection A divided by the probability of B, provided probability of B is not equal to 0. And also, the conditional probability of B given A will also be written as that. That is the probability of B given A, meaning that B occurs given that A has already occurred. And this will also be written as the probability of A is occurring first, so that is A intersection B, and this is divided by the one which is after the given is what we shall be calling, or what we shall be putting in the denominator. So it will be probability of A intersection B divided by probability of A. So meaning that whenever you are given or you are told to find probability of A given B, then you have probability of A intersection B and probability of B. You can easily compute that. So what I need also to inform you here is, if you write this and this one here, probability of A intersection B and probability of B intersection A, they are actually the same, provided the occurrence of A and B does not matter. So you need to know that if you have A intersection B, that this is same as B intersection A, because the outcomes or the members of A intersection B are the same members or the same elements in B intersection A. So for that case, we can also have probability of A intersection B same as the probability of B intersection A. So if you have a probability of B intersection A divided by probability of B, then this one here, instead of writing probability of B intersection A, you can use the same values for A intersection B. So in other words, this one here can be A intersection B or B intersection A. But because B is the first one here, if you are writing it, to write it generally well, because sometimes you may find that the occurrence of A and B matters. So it is important to have this as B intersection A. But when you are looking at calculations, you can still use the same value for A intersection B with B intersection A. So this and this shouldn't be confusing you. They are the same. Probability of B intersection A is same as the probability of A intersection B. So these are what we call the conditional probabilities. And I hope the definition is very clear to us. Now, having looked at the conditional probabilities, let us look at the multiplicative rule, or what we can call the multiplication theorem of probability. So it all comes from what we have already talked about. We had the probability of A given B as the probability of B intersection A divided by probability of B. But as well, we said that this can as well be same as probability of A intersection B divided by probability of B. So having B intersection A, it is same as having A intersection B. So for that case, if I have probability of A given B, which is same as the probability of A intersection B divided by probability of B, so what we can do here is we can easily cross multiply here, or else multiply through by probability of B. It will be the same thing. So if you multiply through by probability of B, then you can easily see that probability of A intersection B is same as the probability of B times the probability of A given B. So you can easily see that from here, probability of B times this. So the multiplicative theorem or multiplicative rule comes from the conditional probabilities. So by making probability of A intersection B the subject. So when you make it the subject here, you will get that, which is this. And as we said, this will occur provided this one here is not equal to 0. In other words, the probability of B must not be equal to 0, or else must be greater than 0, because probability of an event cannot be a negative. So also where this one comes from, this also comes from the probability of B given A. So this is same as the probability of A intersection B are divided by probability of A. Here you are beginning with A because A occurred first. Here you are beginning with B because B occurred first. A given B means B occurred first, then A occurred after B has already occurred. But as we have said, you can have this as same as this. These are the two things are the same. So if I write probability of B intersection A and I write it as probability of A intersection B, it shouldn't be confusing you. So from here also, when you make probability of A intersection B the subject, then you should be able to come up with this expression. So these two expressions are what we call the multiplicative rule of probability. So probability of B given A, this represents the conditional probability of occurrence of B when the event A has already occurred or has already happened. We have talked about this. This is the conditional probability of occurrence of A when the event B has already happened or has already occurred. So this is the multiplicative rule, or what we can call the multiplication theorem of probability. Now let us talk about what we call independent events. So basically, what are independent events? Let us consider this situation. So consider a situation where you are at a party and another situation where it will rain. So you shall note that you are being at a party does not stop a rain. So the fact that you are at the party, it won't stop the rain, because the two are actually independent. The occurrence of one has no effect on the occurrence of the other, or does not in any way hinder the occurrence of the other. You being at the party does not stop it from raining. So those are some of the situations that you consider to be independent. So we would say that the two are independent events. That is, the occurrence of one does not affect the occurrence of the other. Another example is using a pen when it is raining or not raining are independent events. So basically, what is the definition for independent events? So we shall be saying that two events A and B are said to be independent if the occurrence of one does not affect or hinder the occurrence of the other. And for that case, we shall be saying that events A and B are said to be independent if, one, the probability of A given B is same as the probability of A. Why do we say this? Because probability of A given B means that the occurrence that A will occur given B has already occurred. But if A and B are independent events, it means the occurrence of A is not affected by the occurrence of B, because B has already occurred, yes. But in that way, does the occurrence of B has an impact on the occurrence of A? Nothing, because A and B are independent events. So if A and B are independent events, the fact that B has already occurred, it has no impact on the probability of occurrence of A. So that's why we say the probability of A given B is same as the probability of A. And the probability of occurrence of B given that A has already occurred, meaning A has already occurred, but B to occur is not affected in any way by the occurrence of A, meaning that such a probability of B given A will be same as the probability of B, because the occurrence of A, it does not affect the occurrence of B. So the probability of B given A is same as the probability of B. So if these are true, then we shall be saying that A and B are independent events. Now, from a multiplicative rule that we have seen above, just seen above, we can as well say that from the multiplicative rule, where we have said that probability of A intersection B is same as the probability of A times the probability of B given A. We have seen that. And also we said the probability of A intersection B is same as the probability of B times the probability of A given B. A given B. And we are saying that if A and B are independent, then the probability of B given A is same as the probability of B. In other words, probability of A times probability of A intersection B is the same as, since A and B are independent, we are saying this one here is same as this. So if that is the case, then it means this is probability of B. Okay, so probability of A intersection B is same as the probability of A times the probability of B. even here, we are saying that this is same as probability of B times. We are saying if A and B are independent, then the probability of A given B is same as the probability of A, because the occurrence of A is not affected by the occurrence of B that has already occurred. So this is times the probability of A. So you can easily see that in any way, the probability of A intersection B will be same as the probability of A times probability of B, as we have seen in the two cases. So this is what we are talking about. The probability of A intersection B is same as this times that. This is from the multiplicative rule that we have simply seen. But this one here is same as the probability of B, as we have seen in that case, meaning that probability of A intersection B is same as probability of A times probability of B. So whenever we are talking about independent events, we shall be saying that if two events A and B are independent, and then the probability of A intersection B is same as the probability of A times the probability of B. That is what it means for two events to be independent. So for two events to be independent, this is true, this is true, this is also true. However, this don't use this one here, and this, unless you are talking about independent events. This only happens for independent events. Okay? If you are not talking about independent events, don't say probability of A given B same as probability of A. This will be wrong. We have seen that probability of A intersection, probability of A given B is same as probability of B intersection A, or probability of A intersection B divided by probability of B. This one here is what we put here. This is by definition. But when they are independent, instead of having probability of B intersection A, we shall have probability of A times probability of B if they're independent. So that's why this and this will cancel, and you will have this one true. So that's why we can say probability of A given B is same as probability of A. That is only when A and B are independent. Please don't use this definition that probability of A given B. They give you probability of A, probability of B, probability of A intersection B. Then they ask you, find the probability of A given B. Then you simply say probability of A given B is equal to probability of A. If they have not mentioned that they are independent events, don't use this. Use the normal definition, which is this. If you are not talking about independent events, don't multiply probability of A with probability of B if they have not mentioned that they are independent events. Please take note of some of these things. So this is basically a special multiplicative rule of probability of events. As we have seen, this is coming from the multiplicative rule of events. So basically, this is about independent events. But let us look at another scenario where you are having three events. So if you are having three events, when do you say they are pairwise independent? So we shall look at that. So we are saying three events A, B, and C are said to be pairwise independent if and only if each pair of events chosen from A, B, C are independent. That is, A and B are independent, B and C are independent, A and C are independent. What does that one mean? If these events A, B, and C are pairwise independent, then having probability of A intersection B, it will be same as probability of A times probability of B. Having probability of A intersection C, this is same as probability of A times probability of C. Having probability of B intersection C, this is same as probability of B times probability of C. So we shall be saying that A, B, and C are pairwise independent if this one is true, this one is true, and this one is true. And if, in addition to that, if you have probability of A intersection B intersection C, then still this can be written as A times probability of B times probability of C. So here it will be said that such events are pairwise independent. And if this is true, then we shall say they are totally independent. So that is about independent events. And we shall use this same knowledge in proving some of results. So before we come to proving some of the important results, let us first get to understand some of these few things. When they talk about mutually exclusive events, we have already talked about such events, then independent events. You need to take caution of some of these events. So when they talk about mutually exclusive events, we know two events, A and B, are mutually exclusive if A intersection B is empty. In other words, probability of A intersection B is a 0. So A and B will be said to be mutually exclusive. Then independent events, probability of A intersection B is same as the probability of A times the probability of B. But if they don't mention that they are mutually exclusive or they are independent, please don't use any of these. Don't use any of these. So you have to use our previous knowledge, the knowledge that we looked at in our previous lectures. That is basically lecture 3 and lecture 2, where we are talking about how do you get probability of A intersection B, A union B. But if they mention about independent events, then you need to think about this idea of multiplying individual probabilities. If they talk about mutually exclusive, you need to think about having probability of A intersection B as 0. So you need to take note of some of these things. So let us look at some other results. We looked at some other results in our previous lectures, so I hope this one will also be easier for us. So we shall be looking at some of the results pertaining independent events. So we shall be using the knowledge of independent events. So for example, if A and B are two independent events, then A and B complement are also independent events. So you need to prove that if A and B are independent, then A and B complement are also independent. So it is not a must that if the two are independent, then this one here, they have also to be independent. You need to prove that. So that is what we need to look at. So let us look at our result number 1 for this case. So result, that is if A and B are two independent events, then A and B complement are also independent. So here is the result we need to prove that if A and B are two independent events, then A and B complement are also independent events. So we need to prove this. We know that A and B, or we are given that A and B are two independent events. So we are given that A and B are independent events. So if A and B are independent events, as we have already seen, then it means that probability of A intersection B can be written as the probability of A times the probability of B. We have already seen that if A and B are independent, then the probability of A intersection B is same as that. So we shall call this one equation number 1. Now we need to prove that A and B complement are independent. This is what we need to prove. Are independent. So in order to prove that A and B are complement are independent, we have to show that the probability of A intersection B complement is the same as the probability of A times the probability of B complement. This is what we need to show, because we are told that we need to prove that A and B complement are independent. So in order to prove this, we must prove this. And if we prove this, then we shall be able to say that A and B complement are independent. Now let us consider the probability of A. Let us consider the probability of A intersection B complement. If you recall very well from our previous lectures, what is the probability of A intersection B complement? You look at this. This comes from A. This is probability of A only. So A only, if you are having A and B, if you remember very well, A and B, this is B only, that is A complement intersection B. This is A only, that is A intersection B complement. Then this is A intersection B. If you recall very well, when you get A intersection B complement plus A intersection B, you get the probability of A. So I hope you still recall that. So we are saying that the probability of A is same as the probability of A intersection B plus the probability of A intersection B complement. So in other words, if I need the probability of A intersection B complement, I can make this one the subject and bring this one the other side. So it becomes the probability of A minus the probability of A intersection B. If this is true, or if this is okay, we already told that A and B are independent, and thus probability of A intersection B is same as probability of A times probability of B. So having this, now I can say minus probability of A times the probability of B. And this is from equation number 1. From here, you can easily see that this and this are common. So I can put probability of A out, and I remain with 1 minus probability of B. What remains here will be probability of B. And this is still same as the probability of A times 1 minus probability of B. If you recall very well, we said probability of A plus probability of A complement, we actually proved this is same as 1. Then this means that probability of B plus probability of B complement is equal to 1, using the same idea here. So 1 minus probability of B is actually same as probability of B complement. This is same as probability of B complement, because probability of B plus probability of B complement is same as 1. Is same as 1. This comes from probability of B plus probability of B complement is equal to 1. This is why we are writing this. So clearly you can easily see that probability of A intersection B complement is actually same as probability of A times probability of B complement. So from equation 2, we can therefore say that A and B complement are actually independent events. Because we said for them to be independent, then we must show this, which we have shown. So therefore, let us give a conclusion and say therefore from equation 2, A and B complement are independent events. And our result will be approved. Now, we look at the next result, which I believe you would be able to do. So result number 2, our result number 2 for today will be, it is similar to what we have simply done. If A and B are two independent events, then A complement and B are also independent events. This should be easier now, because it is almost similar to what we have done. So where there is A, it is now A complement, and where there is B complement is now B. So we shall use a similar procedures. So let us try that one very fast. So we need to look at the proof. We are given that A and B, are independent events. A and B are independent events. And if they are independent events, then it means the probability of A intersection B will be same as the probability of A times the probability of B. We shall still call this equation number 1. So we need to prove that A complement and B, we need to prove that A complement and B are independent. We need to prove that A complement and B are independent. So in order to do that, we need to show that the probability of A complement intersection B is same as the probability of A times the probability, this is A complement, the probability of A complement times the probability of B. So that is basically what we need to show. So in order to show that, we shall consider our left-hand side. So let us consider the probability of A complement intersection B and see if we shall get this one this side. But for this case, you should be now able to know that probability of A complement intersection B, which is same as probability of B only, is same as probability of B minus the probability of A intersection B. I hope this one is okay for everyone. We looked at that in our previous lectures. It should now be okay. So we are considering now this set. We are saying when you get probability of A intersection B, when you get this plus this, you must get this. So in other words, probability of B is same as like the way we have this. So where there is A, simply put there B. Something like probability of B is same as probability of A intersection B, then plus probability of A complement intersection B. So we are getting this plus this is equal to that. So that is the same case we are considering here. And for that case, we shall have this as probability of B minus, we are told that A and B are independent. And for that case, for independent events, this is true. So minus probability of A times probability of B. So looking at this, you realize B is common. Probability of B is common. So simply factorize it out. Here you remain with 1 minus probability of A. It should now be clear. It should now be clear that from probability of A plus probability of A complement is equal to 1, then 1 minus probability of A should be clear to everyone that this is A complement. So from here, we shall therefore have this equal to probability of B times probability of A complement, which you can easily write as probability of A complement times probability of B. And this is probability of A complement intersection B. When you look at this, then you look at what we needed to prove, which is equation 2. So you realize that we have shown that probability of A complement intersection B is same as probability of A complement times probability of B. So for that case, from this equation 2, hence from equation 2, we can conclude that A complement and B are independent events. And that will also be approved. So another result, that is result number 3. So our result number 3 will be, let's talk about result number 3. It says that if A and B are two independent events, if A and B are two independent events, then A complement and B complement are also independent events. Are also independent events. So we shall be following similar procedures as we have done. So basically, we are given that A and B, we are given that A and B are independent events. A and B are independent events. And if they are independent events, then everyone should be able to tell us that probability of A intersection B is same as probability of A times probability of B. We call this equation number 1. So we need to prove. So we need to prove that A complement and B complement are independent. So in order to prove this, we must show that a probability of A complement intersection B complement is same as probability of A complement times probability of B complement. That is what we must show. If we show that, then we shall conclude that A complement and B complement are independent. So let us consider. for that case, let us consider our left-hand side, A complement intersection B complement. If you recall well, this one by definition, this from De Morgan's rule, we should be able to write this as probability of A union B, everything complement. But we as well know that if you have this is same as 1 minus probability of A union B. Again, we know by definition, probability of A union B is same as probability of A plus probability of B minus probability of A intersection B. By definition, we know that. So if I open this bracket, it will be 1 minus probability of A minus probability of B plus probability of A intersection B. So when you look at this, we are already aware that A and B are independent, and for that case we can have this as probability of A times probability of B. This is from equation 1. We can write that from equation 1. So I hope we are still together. Now from this given point, where we are having 1 minus probability of A, I may try to write it, minus probability of B plus the probability of A times probability of B. I want us to look at this. If you look at this, 1 minus probability of A, 1 minus probability of A, this is probability of A complement. Because we know that probability of A plus probability of A complement is same as 1. Same as 1. So if you have 1 minus probability of A, when you take this one to the other side, then you remain with probability of A complement. So here I'm remaining with minus probability of B plus probability of A. Now I want us to rearrange this. Such that we make it a bit easier. I want us to begin with plus probability of A times probability of B, then minus, I want us to have this minus probability of B. So when you look at this is same as probability of A complement. Now I want us to pull out negative of probability of B. Or else, let us pull out probability of B here. If you pull out probability of B, what remains here? You remain with probability of A minus 1. You remain with that. Now, I want us to look at this. When you look at this probability of A minus 1, I want us to put it in this way, where I can have this as 1 minus probability of A. So in that case, I want us to bring out the negative sign. If you take out the negative sign, this will be minus probability of B. Then what remains here, this was initially a positive, so it becomes minus probability of A, and this becomes a plus. I want to have a minus out, such that it becomes 1 minus that. So in other words, I can easily write this as 1 minus probability of A. I hope that one is okay. So I'm pulling out a minus such that I can have 1 minus probability of A instead of probability of A minus 1. Or else, if you can still, you can also get it from here. You can bring the one this side, you take this one the other side. In other words, probability of A minus 1 is same as negative probability of A complement. Still, it can make sense as well. Okay, so from here, I want us to have this as probability of A complement minus probability of B. But what is this? This is probability of A complement. When you look at this and this, they are the same, meaning I can have probability of A complement out. When I put it out, here it will remain with 1 minus probability of B. And again, 1 minus probability of B is same as probability of B complement. And this is same as probability of A complement intersection B. Probability of A complement intersection B complement. So it is clear that this is same as what we have been wanting to prove, which is this. So from 2, therefore, we can easily say from 2, A complement and B complement are independent. So these are independent events, and you will have proved that. So you must make sure you follow the correct procedures. If you want to prove probability of A complement intersection B complement, so you need to prove that this is same as this. So don't simply put this is equal to that. So you must make sure you start with this side, get what it is equal to from what we have so far looked at, then see how best you can come up with this expression. So we have looked at the three results, and I hope you are able to prove them. Now we want to look at some examples that will help us to master very well the concept that we have so far looked at. That is about conditional probability, then about independent events. So we need to look at some few examples. We have so far looked at conditional events. We have looked at independent events. We have proved some of the result, that is result 1, result 2, and result number 3. So far, we want to come to examples. And our example number 1 says, given that events A and B are such that probability of A is that, probability of B is that, and probability of B given A is 0.1. So let us first have that. So we are told that we have, let us first look at what we are given. So we are given that the probability of A is 0.6, probability of B is 0.2, probability of B given A is 0.1. That is what we are given. And now they need us to find part 1, probability of A intersection B. So how do we get probability of A intersection B? Now, you begin by looking at the information given. This is probability of A. It can't be manipulated. It is already probability of A. Probability of B is already given, 0.2. So we cannot manipulate it further. But we have probability of B given A, which is 0.1. This can be manipulated because let us first consider probability of B given A. By definition, probability of B given A is same as probability of A intersection B divided by probability of A. This is by definition. Here they have not specified whether A and B are independent events or mutually exclusive events. So don't say probability of B given A is same as probability of B. That one will not be true. Since they have not specified, this will be the expression we shall use. Now, from this given expression, you realize that we have probability of B given A, which is this. We have probability of A, but we don't have this. So we can easily get this, since this and this are known. So this is 0.1, which is equal to probability of A intersection B divided by 0.6. So from here, probability of A intersection B will be same as 0.1 times 0.6. So you get the value, that is 0.1 multiplied with 0.6, and that will give us a 0.06 as the probability of A intersection B, and that will be answered. 2, we need to look at the probability of A given B, probability of A given B. So what will be the probability of A given B? So probability of A given B, part 2. So by definition, we know probability of A given B is same as probability of B intersection A divided by probability of B. But as we said, probability of B intersection A is same as having probability of A intersection B. So it is same as having that. A intersection B and B intersection A are the same. So in other words, since the two are the same, you realize that we already have probability of B, we already have probability of A intersection B, which is this. So I will have this as A intersection B 0.06 divided by probability of B, which is 0.2. So get 0.06, divide it by 0.2, and that will give us 0.3. So therefore, the probability of A given B is same as 0.3. So part 2 will also be answered. We shall look at the next part, that is part C, A complement given B complement. Probability of A complement given B complement. So part 3, probability of A complement given B complement. So looking at probability of A complement given B complement, so we shall look at by definition, what does this one equal to? So by definition, everyone should be able to write this by definition as probability of A complement intersection B complement. This is the first, so we can have it like this. So this is A complement given B complement has already occurred, so we can have this as B complement intersection A complement divided by probability of B complement. But as I said, when you have B complement intersection A complement, you can still write it as A complement intersection B complement. So this shouldn't be a problem to anyone. So B complement intersection A complement, you can have it as A complement intersection B complement. Whether you write this or you write this, it will be the same. Such as, what is important is that it is this intersection this divided by what we have here. So this will give us, this will be same as, when I look at what I have here, let me first of all consider each one at a go. So I want to consider first, we'll call this one equation star. I want to consider probability of A complement intersection B complement. This is same as by De Morgan's rule, the probability of A union B everything complement. And what I have to again remind all of us is that don't say that probability of A complement intersection B complement is probability of A complement times probability of B complement, because we proved that it was there in some of the results. But don't put it there, because here they have not said that A and B are independent events. You only do that if they are independent events. I hope that one is very okay. Now, from this given point, this one can be treated as 1 minus probability of A union B. But what is this one here? This is same as probability of A plus probability of B minus probability of A intersection B. And I hope you call this by definition. So this is same as 1 minus, let us look at this. Probability of A is known, probability of B is known, A intersection B is known. So let us substitute them. 0.6, 0.2. So this is 0.6 plus 0.2 minus 0.06. We already had that. So 0.6, 0.2, 0.06. So from here, let me try to simplify what I have in this bracket. So let us get 0.6. We add there 0.2. We subtract there 0.06. So this will give us 0.74. So get 1 minus the answer, and we should be able to get 0.26. This is probability of A complement intersection B complement. Now, from this, we also need probability of B complement. So probability of B complement is the same as 1 minus probability of B by definition, which I hope you still recall. This is 1 minus probability of B. What is probability of B? 0.2. So this is minus 0.2, and this will give us 0.8. So we have got this, we have got that. So we can go on and get the probability of A complement given B complement. So next we shall have from equation star, a probability of A complement given B complement will be same as So we have the probability of A complement intersection B complement as 0.26 divided by 0.8. So 0.26 divided by 0.8. So this will give us a 0.325. So therefore, the probability of A complement given B complement will be same as 0.325. And that will be the answer. So I hope question 1 is very clear to all of us. The most important thing here is make sure you get these ones from definition, because they have not specified whether A and B are independent events. If they have not specified, please don't use some of the results we have seen for independent events or for mutually exclusive events. So let us look at the next example. So two events A and B are independent. If probability of A intersection B is equal to that, probability of A union B is equal to that. Find the possible values. Find the possible values of 1, probability of A, and 2, probability of B. We look at example number 2. So for example number 2, we are given that A and B are independent. A and B, we are given A and B are independent events. If A and B are independent events, then you are also told that probability of A intersection B is a third. We are also told that probability of A union B is 5/6. Now, they need us to get the possible values of probability of A and probability of B. So since A and B are independent events, then it will imply that the probability of A intersection B is same as probability of A times probability of B. That one should be true if they are independent. Now, let us consider probability of A times probability of, let us first consider probability of A intersection B equaling to a third. Since we are told that A and B are independent, then this should be treated as probability of A times probability of B, which is same as a third. And if that is the case, you realize we have two unknowns. Probability of A is not known, probability of B is not known. So to make life easier, I will first let a probability of A to be represented by X, probability of B to be represented by Y, such that X times Y will be equal to a third. So 3xy, if I cross multiply, it will be equal to 1. I will call this one equation number 1. So 2, I will consider probability of A union B, which is given as 5/6. By definition, this is same as probability of A plus probability of B minus probability of A intersection B which is equal to 5/6. When you look at this, you realize we have let probability of this to be X, so I can have this as X plus Y minus A and B are independent, so we can have this as probability of A times probability of B, which is giving us 5/6. So I go on and have this as X plus Y minus this. This is X. Again, this is Y, which is equal to 5/6. So from that, you can as well easily see that we had xy here. So xy is same as a third. So I can say x plus y minus xy is a third is same as 5 over 6. So x plus y is same as 5 over 6 plus a third. So let us go on and try to simplify this. So you are having x plus y, which is equal to, get the LCM, which is 6 divided by 6 is 1 times 5 is 5. 6 divided by 3 is 2 times that is 2. So x plus y is equal to 7 over 6. Now, when you look at this, these are two equations which we can easily solve to get the values of x and y. So looking at these two equations, it should be easy for all of us to easily see that since this is xy and this is x plus y, then I will use what we call the substitution method of solving two simultaneous equations. Now, what we shall do is, from this expression, I will make x the subject. So x is same as 7 over 6 minus y. So I will call this one here equation star. Now, I will substitute this equation. And if we leave this, let us call this one equation number 2, where we have made that one the subject. So I will now substitute x in equation 1. So substituting x in equation 1, we shall have, this is 3xy, but x is 7 over 6 minus y. So this is 3 into 7 over 6 minus y times y, which is equal to so where there is x, we are putting 7 over 6 minus y, then times this y is equal to 1. So this is equal to 1. So try to simplify this. Open bracket, 3 times 7. I'm multiplying 3y here. So 3 over that, 2, 6. We are multiplying by this y, which is out. Then minus 3 times y. Also multiply this y, which is out. It's equal to 1. So by 3 is 1, by 3 is 2. So we get 7y over 2 minus 3y squared, which is equal to 1. So this will be same as, we can easily multiply through by 2. Let us multiply here by 2, 2, also here by 2. So this will be 7y, this and this cancels, minus 6y squared, which is equal to 2. So try to rearrange this one here, bring this one this side. So 7y minus 6y squared minus 2 is equal to 0. So form a quadratic equation. So begin by this, minus 6y squared plus 7y minus 2 is equal to 0. So from that, I want us to multiply through by this negative, to have this as 6y squared minus 7y plus 2, which is equal to 0. I'm multiplying through by this minus. So this will give us 6y squared minus 7y plus 2 equaling to 0. So this is a quadratic equation, which quadratic equation can be solved by various methods. So I will use the quadratic formula, negative b plus or minus square root of b squared minus 4ac divided by 2a. So this is our a, this is our b, this is our c. So our a is 6, b is negative 7, c is 2. So meaning that y is equal to minus b, that is minus 7, plus minus square root of b squared, negative 7 squared, minus 4 times a, which is 6, times b, which is 2, divided by 2 times 6. So this will be same as 7 plus or minus square root of 49 minus, get 4 times 12, that is 48. That is 48 divided by 12. So this will give us 7 plus or minus square root of 1 over 12. So this is 7 plus or minus 1 divided by 12, and this is y. So from here, let us get y. We are having y as 7 plus or minus 1 over 12. So we need to get the values of y. So either y will be 7 plus 1 over 12 or 7 minus 1 over 12. So y will be 8 divided by 12, or y will be 6 divided by 12. So try to put by 4 here is 2, by 4 is 3. Or y is, by 6 is 1, by 6 is 2, 1 over 2. But if you recall, y was representing a probability of b. So we need x. So remember, x is same as 7 over 6 minus y. So I will refer to equation 2. So from equation 2, where we have x as 7 over 6 minus y, so let us consider for y equaling to 2 out of 3. So if y is 2 out of 3, so x will be 7 over 6 minus 2 out of 3. Put LCM, 6 divided by 6 is 1, times 7 is 7, divided by 3 is 2, times that is 4. So this is 3 divided by 6. So we have 3 divided by 6, and this is by 3. This will give us 1 over 2. So x is 1 over 2 when y is 2 over 3. So what does this one imply? This implies that probability, remember, x is representing probability of A. So this implies that probability of A is a half when probability of B is 2 out of 3. So we shall have that one assorted. But we also have when y is a half. So now let us look at when y is a half. When y is a half, what will be x? X is 7 over 6 minus a half from here. So we are putting y equal to a half. By LCM, still 6 divided by 6 is 1, times that is 7. 6 divided by 2, 3 times that is 3. So this is 4 divided by 6. So by 2 is 2, this is 3. So this implies that x is 2 out of 3. So this therefore implies that x is 2 out of 3 when y is a half. So what does this one also imply? This therefore implies that probability of A is 2 out of 3 when probability of B is a half. So from there, it means we shall be able to get the possible values of probability of A. So the possible values of probability of A will be a half and 2 out of 3. A half and 2 out of 3. So the possible values here of this is a half and 2 out of 3. Still the same here, a half and 2 out of 3. So those will be the possible values for probability of A and probability of B. So next, we are told if A and B are independent events with probability of A as that, probability of B as that, find the following. So this should be easier for you now, having looked at some of the questions. You should be able now to try this. So you are told A and B are independent events, and you are given probability of A as a set, probability of B as that, you need to find this. So let us try this one as well. So you are given a probability of A. You are given probability of A as a third, probability of B as a quarter. So this is what we are given. But one, before that, we are told that A and B are independent events. This is very important. A and B are independent events. So you need to find one, probability of A complement, intersection B complement. As we have seen in some of our results, we saw that if A and B are independent, then A complement and B complement are also independent. In other words, the complements are also independent. So A complement intersection B complement can be treated as the probability of A complement times the probability of B complement. So here you have different ways of how you can easily attempt this. Another one would be so if you also put by definition A complement intersection B complement is same as probability of A union B complement. But you must also go ahead and say this is 1 minus probability of A union B. Then again, you first look for this by again putting the definition. Probability of A union B is probability of A plus probability of B minus probability of A intersection B. So this one here should be easier. So you need probability of A complement. So what is probability of A complement? Probability of A complement is 1 minus probability of A. So this should be 1 minus a third. And 1 minus a third should be giving us 3 minus 1 over 3, which is 2 out of 3. Then you go ahead and get probability of B complement, which is 1 minus probability of B, which is same as 1 minus probability of B is a quarter. So this should be 4 minus 1, that is 3, divided by 4. So next you get probability of A complement intersection B complement. So this is A complement is 2 out of 3. B complement is 3 out of 4. So try to simplify this. By 3 goes, by 2 is 1, by 2. So this and this will cancel out. By 2 is 1, by 2 is 2. So this will give us a half. So someone who follows this will go on and say this is 1 minus probability of A plus probability of B minus probability of A intersection B. We'll go ahead and have this as 1 minus probability of A is a third, and this is a quarter, minus probability of A intersection B. Since they are independent events, then this is same as having probability of A times probability of B. So which means you can have this as 1 minus, you have a third, plus a quarter, minus a third times a quarter. So you have 1 minus a third plus a quarter minus 1 over 12. So try to simplify that and see if you'll be able to get the same answer. So possibly when you simplify this, you should be also be in position to get probability of A complement intersection B complement as a so simplify this. Get the LCM here, 1 minus the LCM, and you'll be able to get the answer. So try to simplify this further and see if you'll be able to get that answer. So that is part 1. And part 2, that is A complement given B. Probability of A complement given B. That is part 2. So by definition, this is probability of A complement intersection B. Since this one occurred first, so you should have had this. But as we said, divided by probability of B, this is still same as probability of A complement intersection B. So if you write this or this, they are the same. Okay, so we are told that A and B are independent. If A and B are independent, let us look at what will be the probability of A complement intersection B. From some of the results that we have seen, we saw that if A and B are independent, then A complement and B are independent, or B complement and A are independent. So this can as well be A complement times probability of B. But we do this only when we are told that they are independent. Please take note of that. So probability of A complement, we have it somewhere here. A complement 2 out of 3. 2 out of 3. So this is 2 out of 3. Probability of B is also given somewhere as a quarter. Probability of B is given here as a quarter. So we go on and simplify this. So by 2 is 1, by 2 is 2. So we get 1 out of 3 times 2 is 6. So that is A complement intersection B. So let us now substitute it there. So this will imply probability of A complement given B will be same as A complement intersection B, which is 1 over 6, divided by probability of B, which is a quarter. So let us try to simplify this where 1 over 6 divided by 1 over 4. So this is 1 over 6. When you are dividing, it is same as multiplying by reciprocal. So this will be, let us simplify, by 2 is 2, by 2 is 3. So this will give us 2 out of 3. Meaning, probability of A complement given B is same as 2 divided by 3. And that will be the answer. So far, we have looked at 3 examples. And for that case, you should now be in position to try some of these few questions. As we come to the conclusion of our today's lecture, here are some of the questions for you to try out. So ensure you try these questions out. Use the concepts that we have so far discussed to come up with the solutions to these questions. So some of the answers have been given. Make sure you try to come up with the solution and see if the answers correspond. These answers may or may not be correct, so don't solely depend on these answers. In case there are some of the answers which are not right, please put it in the comment section. And in case some of the questions are not coming out, also try to put it in the comment section. So here we have question 1 and 2, and I hope you have put that one down. Then we come to question 3 and 4. So try to put them out, follow the same procedures as we have done, and see if you are able to come up with the answers. So this is 3 and 4. And lastly, this is question 5. In our next videos, I will be coming up with some of other questions that you will need to try out. Make sure you try as many questions as possible. Don't leave any of the questions unanswered. Otherwise, this marks at the end of our today's session. Make sure you give it a like. Don't forget to share, and don't forget to subscribe to this channel. Thank you for coming up to the end of this video. We meet in our next lecture. Bye.